Hi, it's time for another math easy solution. Today we're going to discuss the second part of my example 1 video series on the Gompertz function, which is another model of population growth. And this time look at part D of that. So in my last video I went over parts A, B, and C of this example. So make sure to check that video out to get caught up on this. So basically this is the differential equation that is used in and then when you find the solution of this differential equation, it's the Gompertz function. And also in this video I'm going to go over a brief history on Gompertz, on Benjamin Gompertz, that's his first name. So basically let's just go from there, and I'll quickly recap in parts A, B, and C. So we have this equation, dp over dt equals c times ln k over p times p, where p is population, c is a constant, and k is the carrying capacity, which also is a constant. T is just time. Part A states solve this differential equation to get the Gompertz function. Part B, it finds the limit as t approaches infinity of the population. Part C says graph it for these specific parameters and compare with my earlier video on the logistic equation. And then states what are the similarities and differences, etc. And now part D is basically stating from my earlier video titled differential equations, population growth, logistic equation example 2, I showed that the logistic equation grows fastest when the population is at k over 2, or half the carrying capacity. In part D it states use the Gompertz differential equation to show that the Gompertz function grows fastest when p is equal to k over e. So instead of k over 2 you divide by the number e. So again, recap part A, this is the solution, this is the Gompertz function. I'll write this down. So that's the Gompertz function, it's a solution to that differential equation above. And then the limit of this as it approaches infinity, it's not infinity, this is k, my mistake. So the limit as p of t approaches, as t approaches infinity, the population approaches the carrying capacity k. I went over this in the last video. And then part C, for those specific parameters you had, this was k is 1000 divided by 100, this is just 10. And yeah, basically what we get is this is the Gompertz function with those specific parameters. And then you recall from our earlier video, the logistic equation, we had this. When you graph them out, it looks similar, and this is the carrying capacity k. They both approach it but never actually reach it. So this is k equals 1000. Yeah, alright, so now let's go over part D and solve it. So we want to show that the Gompertz function grows fastest when p is equal to k over e. So to do this, wrote this down, so part D, recall the first derivative test for determining local minimum and maximum, or local max and min. So I'll put the video link to this in my earlier video, put this in the video description below. Basically recall that if you had, let's say this is the x axis like that. Let's say you had at this point, so at this point we had the derivative, just recall the derivative here is 0. So if this part is 0, then basically what you would do is compare, this is called the critical point, and you would compare the derivative to the right of it as well as to the left of it. So if to the left of it was negative or less than 0, and the right side is positive or greater than 0, what you end up having is the function goes downwards and then starts increasing. So this is a 0 derivative, flat line, and then it starts going up, but it is decreasing before. So this is a local minimum. So local min. And otherwise, if it was instead you had a plus, so you had the derivative increasing initially, so it was positive or greater than 0, then it goes to minus 0 at this point. What you end up having is it's increasing, so the function is increasing and then decreasing. So you had here a minimum, or a local minimum. But if you had a negative, then a negative, and then it's 0 in here, so basically it's decreasing, and then it goes to flatlining, still decreases. So there's no local min or max here, that's just an inflection point. Same thing with here, if you had positive and then positive, you're just going to increase, flatline, increase. So this is how you would use the first derivative test. So first thing you would do is find the derivative and then check the signs onto the left and right of these critical points when this is equal to 0. Yeah, except in our case, we need to find the maximum population growth, or the growth rate. I'll just write that better. So maximum population growth rate, we'll call this, I'll just ignore this, or add to the dictionary. So what we're looking for is the maximum of the derivative, which means we will be dealing with the second derivative instead of the first, but it's still the first derivative test. You could think of it as a relative first derivative test, because instead of trying to find out the maximum function size f, this one we're looking at the maximum population growth of the first derivative. So to find out the first derivative, you need to look at the second. To find out just the regular population, you need to look at the maximum of the, you need to look at the 0 point at the growth rate, or the first derivative. So since we're trying to find out the first derivative, we find out the second derivative. So we do the exact same thing as the first derivative test, but for the second derivative. So first thing we need to do is, well, let's just type out our derivative. So we have the function dp over dt. This equals to a simplified p prime, and this equals to our differential equation c ln k over p, and then p. I'll just scroll all the way up, and then yeah, so that's what our function is. Our differential equation dp over dt equals c ln k divided by p times p. So scroll back here. So let's simplify this further, put this cp in front like that, and now what we end up having here is, just put that in there, and then we can use logarithmic property rules. When you have a division, you could subtract these, so this becomes ln k minus ln p, like that. So yeah, so we have this, so it's easier to deal with, and you can see the proof for this in my logarithmic properties video. Put that in the video link below. So you have this, and now you just take the derivative to get the p double prime. So what we have here, you need to use the product rule. So we have cp, derivative of that is just cp prime, and then times this by ln k minus ln p, and then by product rule we just type in cp, or write cp, and now we take the derivative of the inside function here, and the derivative of ln k is just 0, those are just constant, or k is just a constant, and then negative ln p derivative of that is, well, what we end up having is 1 over p, but then use chain rule, derivative of p is p prime, so we have something that looks like this. So now we could expand this further. We have now cp prime ln k minus cp prime, type this in, and then this is going to be ln p, and then finally what we have on this right side, let's expand this further, we have this c, and then these p's cancel, so then this is going to be cp prime, this is canceled with that, and now we can just factor out the c primes all together. We get now cp prime, yeah, we could have actually just simplified this further and instead of expanding it by using logarithmic properties there, but it's let's look at the same answer. So what we have now is cp prime ln k minus ln p. Yeah, same, back to this point again, but now we take this one out, so we have a minus 1, and now we apply that same logarithmic property to combine these two. So what we get is finally cp prime, and then put a square bracket ln of k over p, so your subtraction is a division for the logarithmic, then minus 1, like that, and then square bracket. So now that we have this, but we also know our p prime is just this function, so we could plug that into here. So what we get is, well, there's a c times c there, we'll have a c squared, so c squared ln k over p, and then this is going to be, well, there's a p, I'll just put that p in front just to make it simpler, times p, and then this is going to be now ln k over p minus 1, like that. So yeah, this is our p double prime of t. Let's write it like that. Let's write this neater. So p double prime of t. So now the next step is basically set this equal to 0. So when we set this equal to 0, what we end up having is the only way that it can equal to 0 is if, yeah, well, let's get into that first. So if we set this to equal to 0, what we have now is the c squared, that's just positive. P, the population, we'll assume you have a positive population, so no sitting as negative. So then these two are a positive. And then here, we're actually, instead of saying positive, what we have, P double prime of t equals to 0 if, so this only way is if this P is equal to 0. If P equals to 0, that's one way, or we have this here, K over P. If we have ln, I don't know why it's keep moving back like this. Yeah, so it's either equal to P is equal to 0, or we have this ln K over P is equal to 0. And this is only possible if this inside here, if you recall the logarithmic function, how it looks like, if we have equals to ln of 1. In other words, we have P is equal to K. So we have these two, P equals 0 and P equals K. These are just the equilibrium solutions right here. I'll just write these down. These are the flat line equilibrium solutions, which don't tell us too much. And then the other part is if this part here is equal to 0. In other words, we have, otherwise we have if ln of K over P is equal to 1. So if this is equal to 1, then that means you have 1 minus 1 is 0. And this is true, well, if we just take e to the power of both sides, this cancels, so we get a K over P is equal to e. Rearrange this, and then what we have is P is equal to K over E. So this is the only non-equilibrium solution. And I'll go back to the graph of this. Basically, the two equilibrium solutions are you have this 0. So when you have a 0, there's no population, it's not going to grow. Then when you have the equilibrium as 1,000, which equals to K, and it's a flat line. So outside of those, we have the only other critical point that matters is this one here. So what we'll do now is to check the interval, well, the non-trivial interval, basically check where P is less than K greater than 0. Yeah, so for this interval, what we have now is the derivative, or the second derivative. Yeah, this equals 2 c squared P ln K over P, and then this is times it by ln K over P minus 1. So now we have to look at the signs of them. But first of all, so here the c squared is positive, the P is positive, so we have this right here is positive. And then what we have on this other side here, this K over P. Yes, since P is is less than K, this number is greater than 1. So as I explained here, if it's greater than 1, what you actually end up happening is this is greater than 0. So this means this is positive whenever you have P less than K greater than 0, like that. And then on this side here, this is the only thing that can change. Just because this is greater than 0, or ln K is greater than 0, does not mean that this is greater than 1. So this one we don't know, and that's where we look at the first derivative test. So let's look at that same graph. I'm in the same axis, we'll write P. So yes, so let's move that down here. So now this P, let's look at the interval from 0 up to K over E. K is about 2.618, I think, which is greater than 2. So when you divide it, it's going to be less than actual half. So then the K is going to be something like that over there. So at this point here, we know that P double prime is equal to 0. Yes, so now what we need to check is the derivative to the right of it and to the left of it, or the second derivative to the right and left, and for these two intervals, so 1 and 2. So what we have here for 1, we have P is less than equal to K over E greater than 0. So what we could do here is, well, we have to make it look like ln K over P. Easiest way is just multiply every single side here by, so you multiply this one by E over P. And the reason we're doing this is so that we can have this e cancels with this, and then we end up having a k over p factor, just to see where it goes, because the idea is to find out if it's greater than 1 or less than 1. So when we multiply this outside, we get 0. 0 times that is still 0. The p's cancel, so e less than, now we have this k over p like that. So now we have this. Now we want to make it look again like this ln k over p, just ln both sides, or ln the whole thing. And ln 0, this one, well, that's, if you recall logarithmic property, logarithmic graph, this approaches negative infinity. And then less than e, ln e is just equal to 1, as so yeah, this equals to 1, and then on this side here we have our ln k over p. So now this makes sense why doing this way. I just like this way, it's really quick. You just multiply the entire inequality. So now that we have this ln k over p is greater than 1, that's all we needed to find out. So if it's greater than 1, then we have this ln k over p minus 1. So we have thus ln k over p minus 1. If it's greater than 1, then we have a greater than 1 minus 1. That is greater than 0. In other words, we have the second derivative is greater than 0 at this point. So what we have is a positive. Yeah, so as explained above, since this is greater than 0, actually I'll just write that down here. So we have this p double prime, put a positive. Yeah, so it's positive, or I'll just write p double prime is greater than 0 here. And then now we have to just check this side. I'll put the positive as well there. So now look at part 2's interval. So for 2, we have p is less than k greater than k over e. So again, make it look like the ln k over p. So to do that, first we multiply this by e over p, so that this cancels, we get the k over p. So multiply this on every single thing, we end up getting the e's cancel, so k over p less than, p's cancel, e less than, this one's k e over p. So anyways, now we take the ln of every single side, so we're not changing everything. So we just do that. Now when we take the ln of everything, we have this ln of k over p. So that's the one we need to look at. And then this is going to be again ln of e, which equals to 1. And this is less than ln of k over p e. So now we have this. So this means that this ln k over p is less than 1. So this means that ln k over p minus 1 is, well, this is going to be less than 1 minus 1, less than 0. And in other words, p double prime is less than 0. So we have this is less than 0. So we go from positive to negative. In other words, we get a local max. So we go from going increasing, so the second derivative is increasing, and then at this point is the k over e. P equals to k over e, and then it starts decreasing. So this is a maximum here. So in that interval, it's a maximum. So there's our answer. Yeah, so when we just scroll down here, so thus since this p double prime is positive from the interval 0 to, so p is greater than 0, less than k over e, and it's negative from k over e to k, so in between that, this means that the p prime, or the growth rate, is a maximum, and this just means that p grows fastest when p is equal to k over e. Yeah, and this is it again, so that's the fastest growth rate, as opposed to the logistic equation where it's k over 2. And now one more thing on this part, note that, well, for p is greater than k, so for this case, if we had p is greater than k, look at the interval, we'll call this interval 3 here. So what you have for p is greater than k, this means that, well, our ln of k over p, since p is greater than k, we have this number is less than 1. Whenever it's less than 1, the ln is negative. So this is less than 0. So if it's less than 0, so thus what we end up having is thus the first derivative p prime, which equals to c ln k over p of p. So then this inside is less than 0, so this means it's 0. So the growth rate is decreasing. In other words, the function or the population is decreasing, and the difference is here is that the second derivative p double prime, this equals to, well, c squared p ln of k over p. Then we have the big fraction ln, big part right here, k, and this ln k over p minus 1. Since this part here is less than 0, this is a negative. And now since we have a less than 0 minus 1, that's going to be also negative. So we have two negatives, which makes it a positive. So this is greater than 0. So this means that the second derivative is greater than 0, but the first derivative is less than 0, so it means it's decreasing, except the rate at which it's decreasing is actually slowing down. So it's decreasing at a slower rate over and over again, and you can graph that here. So if you had start off a number greater than 1,000, like let's say 1,200, you're going to be decreasing at a fast rate initially, but then slowly leveling off. In other words, the second derivative is getting bigger and bigger, except the first derivative is still less than 0. And yeah, the second derivative, that doesn't mean it's getting bigger and bigger. It just means yeah, I should have stated better. It's negative. It's positive. The second derivative is positive, so that the rate, as you can see, it's flatlining, so it's not decreasing as fast. But it's still decreasing because it's a negative derivative. So that's all for this part of the part D of the question. But now what I want to go through is a brief history. I'll still delete this. I'll delete this empty space. Let's go over a brief history on Benjamin Gompertz. This is something I usually do whenever dealing with a formula that was invented by a popular, famous mathematician or whatnot, or historian, or physicist and biologist, etc. It's pretty good to get a better idea of who's coming up with these pretty interesting math formulas and concepts. Basically, brief history. Benjamin Gompertz lived from 1779 to July 1865. Was a British self-educated mathematician. That's actually similar to me. I teach pretty much myself. I've had some schooling, but I just do this mostly on my own. And actuary, and I'll get to actuary. Actuary is just a business professional dealing with risk management, risk measurement, management, and uncertainty in economics, etc. Who also became a fellow of the Royal Society, or FRS for short. So FRS, the fellow of the Royal Society, is an award and fellowship granted by the Royal Society of London, London, England, to people that make substantial contributions to the improvement of natural knowledge, including mathematics, engineering, and medical science. He is best known for his Gompertz law of mortality, which is a demographic model he published in 1825. The Gompertz law is better referred to as the Gompertz-Makeham law, which is the sum of an age-independent component and an age-dependent component. I'm not going to get too in detail about it, but the age-independent component is named after William Makeham, and this guy Makeham was also an English actuary and mathematician, and lived from 1826 to 1891. And the age-dependent component is the Gompertz function that we dealt with. So it's a combination of that one we dealt with plus this age-independent one that this Makeham introduced into it. So now the Gompertz function, or Gompertz curve, which is the one that we solved for this video and last video, is based on the assumption that a person's resistance to death increases as his years increase. Actually, I wrote that wrong. This is decreases. So Gompertz function is based on the assumption that a person's resistance to death decreases as his years increase, and that's why the function ln is used, and then ln function looks something like this, where you're increasing initially, but it is leveling off later on. And also by the graph, you could see by the graph, you have so initially you have a slow growth, you have a fast growth, and it just decreases as it ages. So that means the population or the person's likelihood to procreate as it gets older drops when he gets really old. So let's go back to this. So it's decreases as years increase. That's his basic assumption. And the model is a refinement of a demographic model by Robert Malthus. And Malthus was an English cleric, scholar influential in the fields of political economy and demography. And basically, political economy is just the study of production and trade and the relations with law and custom and government, as well as the distribution of national income and wealth and otherwise tax distribution, etc. So anyways, the Gompertz function model was used by insurance companies of his time to calculate the cost of life insurance, basically just to see the population size, etc., and how much money you're going to be paying later on. And it's also used in many areas to model a time series where growth is slowest at the start and the end of the period. So yeah, that's pretty much it. It's also called an S-curve type function, because it resembles an S curve, as you can see from here. Yeah, it looks like an S, so like this. So anyways, that is all for today. If you learned from this pretty extensive part D video, I wanted to do this one separately because otherwise the previous video would have taken forever to do. But anyways, hopefully you followed through. It's pretty interesting. Hopefully you learned from something new about the Gompertz function and Benjamin Gompertz and some interesting mathematicians from a while back. I'm still using those formulas. Anyways, that's all for today. If you learn, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.